Good day, everyone. Today we're going to start talking about Chapter 6 in your textbook, which is titled Ionic and Molecular Compounds. This chapter actually starts off by focusing on the career of pharmacy technician because it is very important for pharmacists as well as their technicians to understand the roles that chemical bonding play in medications. In section 6.1, that's where we start talking about ions and how ions require a transfer of electrons. And so, again, this chapter is on ionic and molecular compounds. You'll notice when we say ionic, we're talking again about that transfer of electrons. And generally, your ionic compounds will be ones that contain metals and a nonmetal. Now, if you'll remember, we find our metals on the left side of the periodic table, and we find our nonmetals on the right side of the periodic table. When we move into talking about covalent compounds, though, another way that we can describe covalent compounds is by using the term molecular compounds. And unlike ionic compounds, there is no transfer of electrons in molecular compounds because your electrons are being shared between two different atoms. And so we generally find molecular bonds being formed between two nonmetals, two or more nonmetals. Now, when we are talking about, again, with our ionic compounds, please remember that most atoms, in order to be stable, are trying to get to 8 valence electrons, or they want to get an octet. And that rule is known as the octet rule. And so when you're dealing with compounds, you've got to try to set yourself up so that you give every element what it needs to be stable, ultimately getting to that octet if it requires an octet, or getting to what it needs to be stable. So the next thing that we talk about in this chapter is your positive ions or your cations, which means that you have lost electrons. So again, when you lose electrons, that means you end up with a positively charged ion. Well, why is that if I lost electrons? Well, a loss of electrons now means that I have more protons than I have electrons. And so, since I lost electrons, that positive charge is going to be overwhelming towards the negative charge. Because remember, in a neutral atom, the number of protons and electrons is equal. But when I start taking electrons away, I end up with a positive charge remaining on my ion. When I gain electrons, I form a negatively charged ion or an anion. Now, the biggest thing that you need to remember, again, is we're talking about how many protons and electrons we have in relationship to one another. If you have more protons, then you'll be a cation. If you have more electrons, then you'll be an anion. You also need to remember that generally on the periodic table, metals will form your cations. They will lose electrons. So metals, those elements that are on the left side of the periodic table, they're going to lose electrons. And your nonmetals, those elements on the right side of the periodic table, they're going to gain electrons because they're trying to get to 8. Now, again, when you have positively charged ions or cations, what they do is they give away electrons. And they give those electrons away so that they can get 8 valence electrons. Your book actually talks about the element sodium and how you'll notice that sodium is in group 1A, which means that it has 1 valence electron. What does it mean to be valence? Please remember, that's the electrons that are in the outermost energy level. So if I have 1 valence electron and I'm sodium, if I lose that 1 valence electron, that means that that next energy level will now be full. Okay. And so because it's easier for me to lose that 1 than it is to gain 7, I'm going to lose that one electron and end up with my positive charge. And when we say charge, we're talking about that number that you put at the top right that shows me how many electrons have been gained or lost by an atom to become the ion. Again, when we're talking about our anions, again, they're going to gain electrons, and they're going to gain electrons so that they can get to 8. So if we consider an element like oxygen, oxygen's in column 16 or column 6A, which means it has 6 valence electrons. And so what's it going to do to get to 8? Well, it wants to gain 2 electrons so that it can get 8 valence electrons. And so your nonmetals that are in column 16, they're going to have a 2 negative charge because they're always trying to get those last 2 electrons so that they can get to 8 valence electrons. Now, you can also determine the ionic charges of some elements based off of the groups they are located in. For example, again, if I'm located in group 1A, I'm going to have a 1 positive charge because, again, all of those elements have 1 valence electron. It's easier for me to lose that 1 valence electron than it is for me to gain 7 so that I can get to 8 for my octet. So your group 1A is going to have a 1 plus charge. Your group 2A is going to have a 2 plus charge. And generally, if you are a metal and you're in group 3A, you're going to have a 3 plus charge. Now, I'm going to caveat that group 3A. The element I'm specifically thinking about is the metal aluminum. And again, we know that is a metal. Now, some of those other metals, we'll talk about them in just a moment because they're charge actually varies, and we'll talk about why that happens in just a little bit. Now, if I'm in group 7A, and you'll notice that 7A is all nonmetals. If I'm in group 7A, I've got 7 valence electrons. My goal is to get to 8, so the easiest thing for me to do to get to 8 is to gain 1 electron. So everything in 7A is also going to have a 1 negative charge. Now, you'll notice there are some groups that I skipped, and we'll talk about why I skipped those in just a minute. But again, those charges will vary because of where they are located on the periodic table and what those particular elements do to get balanced. Now, your textbook on page 173 talks about some important ions that are found in your body and what those ions do. And you, if you will, please remember you have to intake these ions daily or you can have disastrous results. And you've got to make sure that you don't get too little of it as well as not getting too much. So please read that information. It is at table 6.4 on page 173. Now, in section 6.2, that's where we start talking about ionic compounds, and we talk specifically about the properties of ionic compounds. And what you're going to find is that when you are dealing with ionic compounds, because those electrons have been transferred from one element to another, there are very important properties that arise. Now, the properties of this compound or of these compounds can include that these ionic compounds form 3-dimensional structures. These form 3-dimensional structures. They have very, very high melting points. So generally with your ionic compounds, you'll find out that most of those compounds are solids and they're very rigid solids. They have very, very high boiling points as well. It takes a lot of heat to overcome the attractions between those particles, those ions that are in ionic compounds, which again leads to several other properties like high boiling points, high melting points, and some other properties we'll deal with in a little bit. Now, when you get ready to write the chemical formula for an ionic compound, it shows me how many of each ion you have present in a uh, an overall, not molecule, but formula unit of that compound. All right. And so the subscripts will tell you how many you need. But the biggest thing that you've got to remember when you're dealing with ionic compounds is that you have to balance the charges. Whatever positive charge you had, it has to balance out with the negative charge. And we balance those charges by adding subscripts. So I've got two examples of problems that I'd like to do here. The very first thing we need to do to solve these problems is to determine what is the symbol for each of the atoms that we have in this compound. And so we know with magnesium, if we go to the periodic table and look for magnesium, the symbol is capital M, lowercase g. And for nitrogen, that symbol is capital N. Now, the next thing we also have to consider is we have to consider what the charge is for each one of those ions. So if I'm talking about magnesium, magnesium is found in group 2. So we know the elements in group 2 all end up with a 2+ charge. And again, we write that charge at the top right as an exponent. When we move to nitrogen, we know that nitrogen is a nonmetal. And because it's a nonmetal, it's not going to lose electrons and end up with a positive charge. It's actually going to gain electrons and end up with a negative charge. So if you look at where nitrogen is located, it's located in column 15 or column 5A. And what that means is it has 5 valence electrons. And since it has 5, it's trying to get to 8. And so what it will do to get to 8 is it has to gain 3. Now, again, when you are writing correct ionic formulas, you've got to remember that the electrons that are lost by one have to be gained by the other. And so what we do to accomplish that is we insert subscripts that tell us how many of each one we have. Now, generally, the way I teach students to do this is just to look at your numbers. Just to look at your numbers. Don't worry about the signs. So our numbers are 2 and 3. So the question is, of the numbers 2 and 3, what is the LCM? And you will remember LCM stands for least common multiple. And so if I list my multiples for 2, I know my multiples for 2 are 2, 4, 6, 8, 10, and so forth. When I list my multiples for 3, they are 3, 6, 9, 12, 15, and so forth. Now, our goal is to find the smallest number that they have in common as multiples. And so when we do that, we notice they both have a 6. So the question is, what do I have to multiply by this 2 to give me 6? And that answer is 3, and I'll place that 3 as a subscript. And what do I have to multiply by 3 to give me 6? That answer is 2, so I'll place that as a subscript. And so when you write a correct ionic compounds formula, you never ever show the charges. All you do is show the subscripts. And so for a compound made from magnesium and nitrogen, the correct formula for that compound would be Mg subscript 3, N subscript 2. All right, I've got another problem for us to look at in aluminum and chlorine. Aluminum and chlorine. So we know the symbol for aluminum is Al. We also know that the symbol for chlorine is Cl. All right, if you notice where aluminum is located on the periodic table, it's in column 3A, which means it's going to have a 3+ charge. When we notice where where chlorine is, it's in column 7A, so it will have a 1 minus charge. And again, when I consider the numbers, my numbers are 3 and 1. Well, what's the LCM of 3 and 1? Well, obviously that LCM is going to be 3. So what do I multiply by 3 to give me 3? Well, I multiply 1. And remember, we don't show ones because ones are understood. If I wrote the letters, that meant I had at least one of them. All right. And then what do I multiply by 1 to give me 3? I multiply that by 3. And so my correct formula for the compound made of aluminum and chlorine is AlCl3. So again, please remember the goal when you write an ionic compounds formula is to balance out the charge, because the electrons lost by one element had to be gained by the other. Now, your book again has several good examples that you can practice with, or you can pick elements from columns 1 and 2, and then your nonmetals to see if you can write the correct balanced formula for those. And again, the subscripts tell us how many of each one of those we need in order to balance out the charge. Now, in section 6.3, that's where we go to naming our formulas. That's where we go to naming our formulas. And the naming instructions are not that difficult. The very first thing you want to do in your formula for an ionic compound is you just name the positive ion. Now, again, the name does not change. Whatever that element is on the periodic table, that's what you would name it. And then the second rule is you name the negative ion, but you have to change the ending of the negative ion to IDE. And so I've got a couple of examples here for us to practice with. Let's say I've got Na2O. We know that Na stands for sodium, so the name of this compound would be sodium, which is the positive part, the positive ion. We know that O is the negative ion, and we know that O stands for oxygen, but we have to change its ending to IDE, so we would actually change that to oxide. And so the name of Na2O would actually just be sodium oxide. When we look at this next one, notice we've got aluminum, which is Al. So we write that down because that's the positive part. Aluminum. And then the S stands for sulfur, but we've got to change that ending to IDE. So the name of that compound would actually be aluminum sulfide. All right, so most of these are pretty simple, especially when you're doing ionic compounds. Please notice that these names don't tell us how many of anything we have in them. You never ever use a prefix to tell me how many of anything you have in them when you're naming ionic compounds. All right, and so again, most of these are pretty straightforward. We are going to get to some that are a little more complicated right now, because remember I told you there are some metals on the periodic table that have more than one oxidation number. Specifically, those metals are our transition metals. So we're talking about every element that goes from column 3 all the way to the stair-step line on the periodic table. If it is a metal, and it go, even if it's in column 13, 14, 15, those are considered transition metals as well. And so they have more than one oxidation number. And so because they do, we've got to, when we name them, we've got to tell you what the oxidation number is. So the rules really don't change, they just add another step. And so the first thing we want to do when we have a transition metal, and again, we're talking about anything from column 3 all the way over to the stair-step line, is we name the positive ion, but now we have to include a Roman numeral that tells us what the oxidation number is. So how do we know what the oxidation number is? The answer is we use what we know to figure out what we don't. So if they give you a compound that has a transition metal, you will be able to determine the oxidation number of the negative part. You will definitely know it because you'll have to know it to determine what the oxidation number of the positive part is. So when we look at this compound, we know that chlorine is in column 17 or column 7A, which means that its oxidation number is a 1 negative. Now, because in this formula there is a subscript of 2, that means the overall charge from the negative is a 2 negative. But we know that the negative and the positive have to balance one another out. So what balances out a 2 negative? Well, that answer is a 2 positive. And so when we get ready to name this compound, we've got to have a Roman numeral that represents 2 to tell us what the oxidation number of our element is. And so when we look at the periodic table, we know that Cu actually stands for the element copper. We just found that the oxidation number for this element is 2 positive, so we put a Roman numeral 2 after the copper, and then we just named the negative ion, changing its ending to IBE. This is chlorine, so we would change that to chloride, and now we have the name of our compound. When you look at the next one again is a transition metal. So again, I've got to determine the oxidation number. And again, it's the same elements as before. So we knew chlorine was 1 negative there. It has to be 1 negative here. And so because there are 3 of those, the overall negative charge is 3 negative. We know it has to be balanced out. So that has to be 3 positive. So when we name this particular compound, this time it's going to be copper 3 chloride. Now, is there a difference between those 2 compounds? The answer is absolutely. So when you give these oxidation numbers as Roman numerals, you've got to make sure that you have the correct oxidation number. Otherwise, you can cause problems. All right, so when you deal with your transition metal naming, again, you've got to determine what the oxidation number is. You've got to include it in parentheses after that element so that we can correctly write that name. Now, the next kind of naming that your book goes into is your polyatomic ions. And the good thing about polyatomic ions is that when you're dealing with a polyatomic ion, the names of those don't change. The names of those don't change. There is a list of polyatomic ions given on page 182 in your textbook. It is a list that you need to become familiar with. You should be able to write the formulas with the charges and the names of those polyatomic ions. And so when we go to naming these compounds, or actually writing the formulas for these compounds first and then naming, again, we've got to figure out what our charges are if they're not given. So for this very first one, we notice we've got Na, which is in group 1A. We know that group 1A has a 1+ charge. They already gave us this polyatomic ion, which is ClO3 with a negative charge. If I balance those out, that's a 1 and 1. The LCM is 1. And so they already balance out. So when I write the formula for that compound, I don't have any subscripts at all on either one of those other than the subscript that was already on your polyatomic ion. Please remember, you cannot change the subscripts on polyatomic ions because when you do, you change what they are, okay? So polyatomic ions, you don't change anything at all about them because they are already set up. You just work with what you've got. If we look at this one, notice both of these are polyatomic ions. And because of that, they gave us the charge on both of these. Notice I have a 1 positive and a 3 negative. And so my LCM for those two numbers would be 3. So what do I multiply 1 by to give me 3? That answer is 3. And what do I multiply 3 by to give me 3? That answer is 1. And so now I have a polyatomic ion and I need more than one of it. And so because of that, I have to enclose that polyatomic ion in parentheses. And again, whether or not your polyatomic ion has a subscript, if you have a polyatomic ion and you need more than one, you always put it in parentheses. If you only need one, then you don't need any parentheses. And so this would be the correct formula for this compound. And so if we were to name this compound, we would name sodium. From our polyatomic ion list, ClO3, we know is chlorate. And so the name of that compound would be sodium chlorate. The name of this compound, we know that from our polyatomic ion list that NH4 plus is ammonium. And again, we don't change it. We keep it just like it is. We know that PO4 with a 3 minus charge actually stands for phosphate. And so the name of that compound would just be ammonium phosphate. And again, if it is on the polyatomic ion list, you never ever change that name that is given. I've got a couple more over here for you to practice. So if you'd like to pause the video so that you can name those, you can. In just a second, I'm going to show you what those correct answers should be. I know that Ca is calcium. I know that SO4 is sulfate. So the correct name for that compound would be calcium sulfate. For this next one, I know that K stands for potassium. I know that HSO4 is on my polyatomic ion list, and its name is hydrogen sulfate. So the name of that compound would actually be potassium hydrogen sulfate. Now, again, polyatomic ions, you don't change the name, you don't change the charge, you just have to make sure that you balance it out when you write the correct formula. Now, your book then, after polyatomic ions, goes into discussing molecular compounds. Your book goes into discussing molecular compounds. So what do you do when electrons are being shared? And again, the naming rules don't change that much. They do change a little bit, but they don't change that much. But I have them here. You just name your first element. You name your second element. Again, changing the ending of that name to IDE. But now when you're dealing with molecular compounds, you have to go back and add a prefix telling you how many of each one you have. So if you've only got one, the prefix you use is mono. When you have two, you use the prefix di. For 3, you use the prefix tri. For 4, you use the prefix tetra. That is TETRA. For 5, and now the prefixes should become familiar for you. For 5, you use penta. For 6, you use hexa. 7, you use hepta. 8, you use octa. 9, you use nona. And 10, you use deca. All right. So if we're given this example that we have here, this SiBr4, if I wanted to name that, I know that Si stands for silicone. I know that the Br stands for bromine, but I've got to change that ending to IDE. So that would be bromide. But now I've got to go back and put a prefix in to tell me how many of each one I have. Now, with the first element, If you only have one of the first element, you do not have to include a prefix. But if you have one of any other element, you do have to have your prefix. So when I look at my bromide, I see that that subscript is 4. And so the prefix I need for that one is the prefix tetra. And so the name of that compound would be silicon tetrabromide. If I do the same thing for the next one, I notice I've got nitrogen, I've got oxygen, but I'm going to change that ending to IDE. And now when I go back in and put my prefixes, I've got 2 nitrogens, that prefix is di. I've got 3 oxygens, that prefix is tri. And so the name of that compound would be dinitrogen trioxide. Now, this process where I'm going from the name to the formula for a molecular compound is actually a little easier than for an ionic compound because they already tell you in the name how many you have. And so for this one, we've got the prefix di, which means we're going to have 2. It says nitrogen, so I know I'm going to have 2 nitrogens. Then the next one says tetroxide, and so tetra means 4, oxide means oxygen, and so it would be N2O4. And when I do the same thing for the last one, triphosphorus dicoxide, phosphorus's symbol is P, tri means there are 3 of them, oxide is oxygen, dec means there are 10 of them, and so my formula for triphosphorus dicoxide would be P3O10. Again, if you have any questions about these prefixes, they are listed in the review for the chapter so that you can go back and look at them. But now we're going to move into talking about how to draw Lewis structures. When we're dealing with molecular compounds, again, you'll notice that there are not a whole lot of elements on the periodic table that are non-metals, okay? And so because of that, that's why we have those prefixes, because these nonmetals can join in different ways, and we need to be able to tell the differences between those compounds. Well, when we move to talking about Lewis structures, we're talking about how these atoms are joined to one another in a molecular compound, in a covalent compound where I'm sharing electrons. Which elements are specifically sharing the electrons? And so your book goes through how to draw Lewis structures. It does mention that when you're considering the elements or the element hydrogen, remember hydrogen only needs 2 electrons in order to be complete. It does not need an octet. So in your Lewis structure, once your hydrogen has 2, then it's good. All right. And so I'm going to go through the instructions for how you draw a Lewis structure. And if you've got any questions, please let me know. So in order to draw a Lewis structure, let's say they give us this compound NH3, the very first thing you want to do is you need to know how many valence electrons do you get from N and H. And so on the periodic table, you will notice for nitrogen, there are 5 valence electrons because it's in column 15 or 5A. And then for hydrogen in column 1A, that means there's 1 valence electron. But if you'll notice, there are actually 3 hydrogens. So you're going to do 3 times 1, which gives you 3. Now, you're going to add these numbers together to create a pool. You're going to add those numbers together to create a pool. And now what your job is to distribute these electrons amongst the elements in this compound so that everything gets what it needs. And so when you're writing this compound or drawing the Lewis structure for it, please remember that hydrogen will never go in the center, and which means that in the center of this compound, we need to have the element nitrogen. And to that nitrogen, we need to have 3 hydrogens. So I'm going to put a hydrogen here. And again, these three hydrogens have to be connected to this nitrogen. And what you've got to remember is every time you draw a line, you're saying that those elements are sharing electrons. So every line that you draw represents 2 electrons that are being shared. So of our pool of 8 electrons, we've already used 2, 4, 6. So from my pool of 8, I'm going to subtract 6, which leaves me with 2 electrons. And so now I've got to see, does everything in the picture have all the electrons it needs to be stable? And when you consider hydrogen, that line represents 2. That's all a hydrogen can have. That one has 2. That one has 2. But when I consider nitrogen, nitrogen has 2, 4, 6. It wants to get to 8. And so I've got to give it those last 2 electrons so that it can get to 8. And once I do that, I notice I've used all of my electrons in my pool and everything is stable. So this is the correct Lewis structure for this molecule. Now, when I move on to my other example, if I do CS2, please notice I've got to count my valence electrons. So when I count my valence electrons for carbon, there are 4 valence electrons. Notice there are 2 sulfurs. Sulfurs in column 16, which means that there are 6 valence electrons, but notice that there are 2, which means that is 12. And so when I add 4 and 12, that gives me my 16. So in my pool, I've got 16 electrons. So when I go to draw my structure, how do I determine what goes in the center? And it's usually going to be the element that is further to the left on the periodic table or further down. Notice in this case, we're going to have C in the center. And to that C, I'm going to connect 2 S's. And then I've got to subtract out how many electrons I used to connect those 2 S's. Notice I drew 2 lines for 4 electrons, which leaves me with 12. Now, I've got to count how many more electrons do I need to be stable. And so when I count, this S only has 2, which means it needs 6 more electrons to be stable. This C has 2 lines, which means it has 4 electrons already. It needs 4 more to be stable. This S has 1 line, so it's got 2 electrons. It needs 6 more to be stable. So if I add those numbers together, 6 plus 4 plus another 6 is 16, but I don't have 16. I've only got 12 electrons. So what do you do when you need more electrons than you have? And the answer is you actually draw a multiple bond. And when you draw that multiple bond, you've got to subtract out electrons because you used electrons to get that bond. All right. And so then I'm going to put my pencil down. I'm going to count how many more I need again so that I see how many I need versus how many I have. When I count this S, it's got 2 lines now, which means I need 4 more electrons. When I look at my carbon now has 3 lines or 6 electrons, so it needs 2 more. And then that sulfur down at the bottom still only has 1 line, so it needs 6 more. So that is 4 plus 2, which is 6, plus these 6, which is 12. So I need 12, but I only have 10. We want to make this molecule symmetric, so I need more than I have, which is why I'm drawing a multiple bond. So I place my multiple bond, I subtract out my electrons, and now when I count, please notice my sulfur needs 4, my carbon doesn't need any, this sulfur down here needs 4, 4 plus 4 gives me 8, and so I would place my dots so that I use all 8 of those. And now everything in the picture has 8 valence electrons that it needs. And that's how you would draw a Lewis structure. If you've got any questions about this, there are several examples in your book where you're doing single bonds and you're double and triple bonds. And then in the next section, your book talks about electronegativity. Please remember that electronegativity deals with how much the atom attracts electrons in a bond. Um, if you have, we rate this on a scale from 0 to 4. If you have a value of 0, that means you have a low electronegativity. If your value is 4, you have a very high electronegativity. And so element or the element with the highest electronegativity on the periodic table is obviously the element fluorine. It loves electrons the most. And so if you'll notice where it is positioned on the periodic table, it's got 7 valence electrons. It's doing everything it can to get that 8th valence electron so that it can be completely stable. But that leads into whether our bonds are polar or not. And so when you determine the polarity of a bond, you actually have to calculate the electronegativity difference, which means you've got to take the elements in the bond and you've got to subtract their electronegativity. You'll never get a negative answer on this. But whatever that electronegativity difference is, that'll generally give you an idea about the polarity of the bond. When you have very large differences in electronegativity, then you'll more likely than not create a polar covalent bond. Polar meaning that it's charged, and so the electron will be more closely bound to one element than another. And because it is bound more closely to one element than another, it creates what we know as a dipole. And that can actually lead to some of the properties we're going to talk about in an upcoming section of the textbook. In section 6.8, that's where we actually start talking about the shapes of our molecule. And what you need to know is that the shape depends on your central atom and how many pairs of electrons it has around it. And when we say pairs of electrons, we're talking about, do we have bond pairs or do we have lone pairs? You have to count all of those to know how many pairs of electrons there are. And so when you have, and actually I need to take this off. Here we're looking at just how many pairs of electrons there are. When you're considering triple bonds and double bonds, they only count as one pair of electrons. Okay, so when you have, let's say you've got 2 pairs of electrons around your central atom only, if there are 2 pairs and there are no lone pairs, then that shape is always going to be linear. If you've got 2 pairs of electrons and one of those is lone pairs, and when I say lone pairs, I'm talking about dots. When I say bond pairs, I'm talking about how many lines there are. And remember, there are 2 electrons in a pair. Okay, so again, if you've got 2 pairs of bonds around that central atom, none of them are lone pairs, then it's going to be linear. If one of them is lone pairs, it's going to be linear. When you go to 3 pairs around the central atom, if there are no lone pairs, that orientation or that molecular geometry is going to be trigonal planar. If you've got 1 lone pair with 3 pairs of electrons around that central atom, then that shape is known as bent. Or if you've got 2 pairs, then that shape is known as linear. When you go to 4 pairs of electrons around the central atom, but no lone pairs, we call the shape tetrahedral. If there's only 1 lone pair, it takes a trigonal pyramidal orientation. If there are 2 lone pairs around it out of your 4, then the orientation is bent. And if there are 3 lone pairs out of the 4, then that orientation is linear. Now, the biggest thing is you have to have the Lewis structure before you can determine what the shape of your molecule is. And your book then goes into talking about more about the polarity. So if it is a polar bond, there's going to be a large difference in the electronegativity. When it's a non-polar bond, there will be very little or no difference in the electronegativity. So nonpolar bonds, we're talking about things where you've got the same element. Like if I've got H2 or N2, all of those are going to be nonpolar bond because they're the same element, so there's no electronegativity difference. Now, when you talk about polar molecules, you can have a polar bond without having a polar molecule. And in order to know whether your molecule is polar, you've got to consider a number of things, including the symmetry that your molecule has. If your dipoles are all symmetric, then you actually create a nonpolar molecule, even though there are polar bonds there. Now, finally, in this chapter, your book moves into talking about the intermolecular forces. And there are three intermolecular forces that you need to be familiar with. They are your dispersion forces, which are very weak forces. These can be felt by any molecule whatsoever. The second kind that you can experience are your dipole-dipole transactions, which these are only felt by polar molecules. So you need to know if your molecule is polar before you can know if the forces that it feels are dipole-dipole. And then the strongest of these three forces is your hydrogen bonds. And you encounter hydrogen bonds when you encounter compounds that have hydrogen being attracted to either nitrogen, hydrogen and oxygen, or hydrogen and fluorine. And we're talking about those three elements because those three elements have a very, very high electronegativity. And so, because those particles are extremely attracted to that hydrogen atom, then it leads to other properties like higher boiling points, higher melting points. It can create situations where the properties change because there's a lot of attraction between the particles. The particles want to stay together, and so it takes more energy to overcome that interaction. And that wraps up pretty much all of the information that's in chapter 6. You find your concept map on page 204. Your chapter review starts on page 204 and goes to 205. And then you've got some things to help you practice with the concepts in chapter 6, starting on pages 206, 207, going to 208. And then you've got your additional practice questions with your answers. If you need me for anything at all, I know I've covered a lot in this chapter. Please reach out and let me know. I hope you all have a good rest of your day. Thank you so much.